Wait. Okay. Good morning, everyone. This is Amit Bhardwaj, and welcome to the Sri Chaitanya Goshala. So today we are going to revise our physical chemistry in 3 hours, right? So we will see how we can make best use of this time, and let us see. So we will move step by step, like chapter by chapter, and we will try to cover the important points of NCERT, the points from where questions are expected most, right? And where students makes most of their mistakes. So it will be very useful for you. So use it properly and don't miss any point, because some points I will write here, some points I will say. So every single point is very much important. Okay, let us revise physical chemistry. Fine. As I said, we will move chapter by chapter. So we are starting with the mole concept, right? Or you can say stoichiometry. If you see the first chapter, we can call it mole concept because mole is the most important part of this chapter. Stoichiometry you can say, and you can say some basic concepts of chemistry. First chapter, right? It gives 2 to 3 questions in the NEET exam, but it decides the many questions from different chapters. That's why very, very important, right? The small point I'm saying, small point I'm taking from here, the first point is significant figures, right? The easiest part, it comes in physics also, so very important. Like if I will give some examples here, I will give example here and I will ask you, or I will try to find it contains how many significant figures, right? The first one, if I say, like if I'm saying it's 2, 3, 4, 5 centimeter, right? So in this, how many SF we have? So it have how many SF? 4. So what is SF basically? SF is the significant figures are the meaningful digits which we know with certainty and plus one uncertain digit, right? So if you look at this, all non-zero numbers are significant figures, right? So 4 are here. If I go to the B part, you say 3054 centimeter. So all zeros in between non-zero are also significant. So here also I can say 4. Now if you go to third one, see third rule if you go, if I am having here, it's 4530 centimeter. So remember, right side zeros will be insignificant if there is no decimal. Okay, right side zeros will be insignificant if there is no decimal. So in this, if I say we are having how many SF? Only 3. It's very important where students make mistake. And if I go for the next one, if I am taking here 0, 0, 5, 2, left side zeros are always insignificant, even if you have decimal. So here I am saying only how many SF? 2 SF. Next one, right side zeros can be significant if decimal comes. Imagine this one, 45.30. So this time I will take this as significant number, right? Now you can go with the next one. We are having here but 450.00, imagine. Now right side zeros are significant. Why? Because the decimal already comes here, right? So how many? 3 and 2, 5 significant figures, right? Next, if I go, even if decimal is coming, remember left side zeros can never be counted in significant figures. So how many are here? Only 3. Right side is significant, but left side is insignificant. I am saying once again, right side zeros will be significant if decimal is present anywhere in the number, in the given measurement, right? But left side will never be significant. Okay. Next, if I take next one, beta, what is it? If I go for this one, I am saying it's like 4.5 10 to power 3. So don't worry about this part. This 10 to power 3 nothing. Just look at the front part. it's 4.5. So how many here? 2 SF. Don't look at this part, okay? It's fine. Now, next one, if they gave some object, 25 men. If I'm saying here 100 benches. So in such cases, when we are discussing about the specific object, so in such cases they are completely, you can say, significant, and there is, you can say, it is infinite. It contains infinite significant figures, right? So very easy. All zeros are, sorry, all non-zero significant, zeros in between non-zero significant, right side 0 without decimal insignificant, right side 0 with the decimal significant, left side 0 always insignificant. And next I will say, if something 10 to power coming +3, -3, +5, -5, don't look at that part, just use the first one and you can see easily how many SF it have, 2. And when there are objects, so objects is completely finite, or you will say its significant figures are how much? Infinite. Fine. This is little bit about your significant figures. I will say in short, if you are adding, sometimes they give addition, do this addition in terms of significant figures. So your final answer should contain the minimum number of decimal places which are present in the given numbers. Like they gave some numbers, and some of these numbers have 2 decimal places minimum. So your final answer should also have 2 decimal places. Whereas in multiplication division, in that case you will see you have to count total significant figures. So in multiplication division, your final answer must have minimum significant figures which are present among all the given numbers you are multiplying or dividing. So in addition and subtraction, what is important? Decimal places. Whereas in multiplication and division, total significant figures are important, right? So be careful about that. Now the next thing, we can come to the laws. We will be short here. Laws of chemical combination. Definitions definitely you know, but NEET don't ask definitions or don't ask the questions where you have to prove that this given data is explaining or proving which law. It's a very simple thing. If I go little short here, now you say first one is law of conservation of mass. So what it is saying, beta, let us understand. Simple thing. Mass can neither be created nor can be destroyed except nuclear reaction, right? So in nuclear reaction, this law will not work so well. So I am saying it's A plus B, giving here what? CD. I have taken here it's 200 gram, it's 100 gram. It was 0, 0. So the mass of reactant consumed will be equal to the mass of product formed, right? In this case, if I am saying after the reaction these become 0, and here I am saying it is 220 gram. So here 300 consumed. So here definitely 300 should be formed, na? So if it is 220, it is how much? 80. The mass of reactant consumed equals to what? Mass of product formed. I am saying mass of reactant consumed. I am not saying mass of reactant taken. Be careful about these two terms, right? Second thing, if I say this is law of constant composition, right? The next thing is law of constant composition. If you take a compound, if you make a compound from any method, from any reaction, you bring it from any country, from any factory, the compound's formula is fixed. If compound's formula is fixed, then the weight ratio of the elements which are making it will remain fixed. Like if I am taking example of H2O. In H2O, if I look at the hydrogen and oxygen, hydrogen how much here? 2. And oxygen how much? 16. So weight ratio is fixed, na? 1:8. You make water from any reaction, You bring water from any country, from any factory, the formula of water is fixed, H2O, and the weight ratio also fixed. How much? 1:8, right? So I'm saying once again, how NEET will ask the question from this law. They will say, we are making water from this method, from this method, from this method. So here they are discussing about only a single compound. From different statements, they are discussing about a single compound. That means they are discussing about the law of definite proportion, or you can say law of definite composition. When they are discussing about same compound in different statements, that means it is law of definite composition, or you can say definite proportion. Okay, don't waste your time to solve it, to prove it. Okay, NEET can't ask you to prove it, right? The next thing I am saying here, look at this carefully. Its next is law of multiple proportion. It's law of multiple proportion, right? How to find? Again I am saying, we will not prove it, we will not solve the question. In just blink of eye we have to answer here, because NEET is a game of time, right? So law of multiple proportion, they will discuss about the compounds which are made up of same elements. Like example I am saying here, look at this carefully. N2, NO, N2O3, N2O4, N2O5. So they are discussing what is common in all of these molecules. The common thing is all are made up of two same atom, NO, 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 all are made up of nitrogen and oxygen. I will not check anything else. I will say it is law of multiple proportion. If they are discussing about different molecules but made up of same atoms, we will say it is law of multiple proportion. I am saying again, we will not solve it to prove. We will just say, okay, these are molecules made up of same atoms, so I can say it is law of multiple proportion, right? Clear? Definition wise, if you say, if you fix the weight of one element in different compounds, the weight of other elements will be in simple or multiple ratio, right? Very easy. Next one, if you say, we are having here law of reciprocal proportion. Again, how to answer in very short time. Law of reciprocal proportion, right? Now see carefully what I am saying. Here they are writing some molecules. I am saying H2O, right? Here I am saying CH4, and here it is CO2. There are three molecules, and these three molecules are made up of only three elements. What I mean, A make compound with B, B make with C, and then A make with C. I will not check any ratio, I will not do any time waste. Look at this again. In this compound, H is combining with O. Here H is combining with C, right? And here you see carefully, again finally C and O combine with each other to make the third compound. Again I am saying, I have A, B, C, three elements. First compound is A and B. Then a compound of what? B and C. And then a compound of what? A and C. Without checking, you can answer very easily. Three molecules made up of three elements. A with B, B with C, and A with C. Okay, they will not go in details. So easily you can answer three molecules, A with B, B with C, and C with A, right? That's it. The next one, if I say beta, it's fourth one. It's Avogadro law. Clear? So what is Avogadro law here? Right? So if you see, I am having here a box. Here I am having a box. These two boxes are there. Here I am saying the volume of box is V. Volume of box is V, temperature T, pressure P. Volume V, temperature T, pressure P. And here I am saying I am having CO2 gas. And here imagine we are having O2 gas. So what this law is saying? This law is saying all the gases in similar conditions of pressure and temperature, if you take their equal volume, so they will contain equal number of moles of the corresponding gases, or they will contain equal number of molecules. What I mean, if I am saying here, it contains X moles of CO2 gas. It contains X moles of CO2 gas, so without anything I can say here that it also contains what? X moles of O2 gas. If volume is same, temperature same, pressure same, then both will contain equal number of moles. Equal number of moles you can say, equal number of molecules you can say, but not the equal number of atoms. Because atoms will depend on the atomicity. How many molecules? X into Na, X into Na. But how many atoms? Into 3, into 2. So moles are same, molecules are same, but not the atoms, right? So atoms you can't say, right? That's it. Now the next one, if I say Gay-Lussac's law of volumes, right? So what it is saying, beta? Very simple thing again. If I am having N2H2 ammonia, so stoichiometry is clearly telling us that if I take its 1 mole, I need 3 mole of H2 and it will make how much? 2 mole of ammonia, right? So if you write this stoichiometry in terms of volume, I can say 1 liter N2 required 3 liter H2 and will form how much? 2 liter of what? Ammonia. Or I can say 1 ml, 3 ml, 2 ml. So the molar ratio and the volume ratio will be what? Same, first of all. And what this law is saying, that if two gases combine or form in a chemical reaction, they will do so in a simple whole number ratio, right? What is the meaning of that? Simple ratio, 1:3:2. It's not very complicated. Simple whole number ratio you can take, right? And the ratio will be same as of what? Molar ratio. So this is it, a little bit about the laws, right? Now let us come to the point. We are talking about the mole formulas. Mole formulas are most important from this chapter, right? Mole formulas will come in every chapter, I am saying. In every chapter of physical chemistry, it is basis for everything of physical chemistry. In many chapters, it will come. We have 3 formulas, so we will write here in short, right? Like first one, if they give me number of particles, and I have to find the mole, how I can find beta? I have to find mole. I will divide number of particles by the Avogadro number to get the moles. Reverse way, if I want to convert mole into particles, I will multiply by Avogadro number. Fine. Next thing here, if they gave me weight, given weight, right? So how I can make moles? I will divide given weight by the molar mass, and reverse, to get the weight from the moles, I will multiply by molar mass, right? Next thing, if I say, if I am having volume here, what do we have here? Volume, right? What we'll do? We will divide the volume by 22.4 to get the moles, and reverse, mole to volume, how? We will multiply by what? 22.4. Clear? But one thing is very important here. What is very important thing? Volume, this formula is only for gases. And which conditions you can say? NTP or STP you can say, right? The third formula is applicable only for gases. This is not for liquid. What cheating they do sometime? They gave us, I am having 100 ml of water, find the moles. No, it is, this third formula is not applicable for liquid volume. You can apply it only for gases. So we have 3 formulas here very clearly: number of particles to mole, volume to mole, weight to mole. And volume, this third formula is applicable only for what? Gases, right? So be clear about this. Don't make a mistake of this type, right? So if we think about it little bit, if we take the question, I am giving a very simple question from here, try to answer. I am saying here, We are having, imagine 80 gram. I am saying 80 gram of methane gas is given to me. 80 gram of methane gas, right? And what they're asking from us? Imagine they're asking first, find number of methane molecules. They're saying find number of methane molecules. Second thing they're asking volume of methane gas. They're asking volume of methane gas at what? At NTP. NTP or STP you can take. NTP, STP are almost same thing. NTP means normal temperature and pressure, and at NTP the pressure we take 1 atm and temperature how much? 0 degrees Celsius, or you can say 273 Kelvin. But if we talk about STP, what's STP? In STP pressure is 1 bar, okay, almost 1 atm only, you can say that. So NTP, STP both are okay for us. But NTP is this formula, the third formula is actually at NTP. At STP though we should go for 22.7, but as I said the change is negligible, so you can take in both cases NTP or STP. In normal books they write always STP, STP, okay, they don't write the NTP word, but STP also fine for us. The number of CH4 molecules, and they are asking volume of CH4 gas. They gave us weight. From weight we can come to moles. Moles to what? Moles, and then from mole we can come where? To the volume or to the number of particles. Let us see how we can do that. Convert this into moles, right? So what is that? Given weight by molar weight. It's 80 by how much? 16. Molar mass na? How many moles coming? 5, right? Okay, good bache. Right answer. Suresh, right bacha. So number of CH4 molecules we can say here, it's 5. Now number of CH4 molecules, so 5 into Na, right? And number of volume of CH4 gas, 5 into 22.4 liters. Okay, very easy. Again I am saying one simple example. Like here I am saying, if I am having here, this is 11.2 liter of helium gas. 11.2 liter of helium gas. The question is to convert into mole, then into number of molecules, and then into what? Weight. So we know it very well. How we can convert volume into what? Moles. Divided by 22.4, right? So how much coming? Half moles. I am giving in terms of arrows. 11.2 liter, we got the half moles. Half mole of helium gas means how many molecules beta? I can say half into Na. So many helium molecules, right? And second thing, if we had to find the weight also, how we find? We multiply by what? Molar mass. What is molar mass of helium? I can say 4 gram per mole. So how much coming from here? 2 gram. So it's very simple to use these three formulas and connect them with each other. If you want to go from volume to weight, volume to number of particles, you have to use mole as a junction. So use it simply. Very, very important formulas, right? The next thing I will take here, the next point is our, you can say, limiting reagent. So what is limiting reagent? It is the reactant in the given reaction which will finish first and decide or limit the amount of product formation. Remember, limiting reactant will always decide the product, not the excess reactant. So first our target is to find what? Limiting reactant, and after finding the limiting reactant we have to move forward, right? Like if I am saying here, imagine I am giving some example. Here we have, it's a, you can say 3A, 2B, and here we have C, and it is making 4 of D, imagine. And at the time 0 means initial time, imagine I am saying here we have 10 moles of this, right? we have its 10 moles, and imagine I am saying we are having its 5 moles, and here I am saying we are having its 2 moles. Okay, these are 0 initially. So they will ask you at the final moment what is the amount of all of these, right? Very common question. Every year in the NEET exam they are asking one question from limiting reactant, and simplest question always, N2H2 ammonia, reaction also fixed, right? So how to find the limiting reactant? First we should know, we can use the shortcut beta, how to find the limiting reactant. What is the shortcut here, right? Shortcut is to take the given moles, divide by the coefficient, stoichiometric coefficient 10 by 3. Given moles 5 divided by coefficients, given mole divided by coefficient. So out of these now I have to select which one is the smallest number. 10 by 3 almost 3.3, 5 by 2 how much? It's 2.5. 2 by 1 how much? 2 only. So you can see here it is least number, it is the smallest number, right? It is smallest number, it will decide it is the limiting reactant. Now its work is done. Come to the main part. Now we know that it is our limiting reactant. Fine. First we decided what is our limiting reactant. Now we'll get the product. Look at this. 2 become 0 because it is limiting reactant. Now 1 of C makes 4 of D. So here 2 are consumed. So 1 makes 4. 2 makes how much? 8. It will make 8 moles. Very easy. Now they can ask you how much excess will left. Look at this carefully. 1 consumed 2. So 2 consume how much? 4. So after going 4, still how much remaining excess here? 1 mole. Here 1 consume 3. So 2 consume how much? 6. So after 6 going, how much left here? 4 moles. So this way you can get the product also and the excess reactant left. I am saying once again, what is the shortcut here? Given moles divided by stoichiometric coefficient. Given moles divided by stoichiometric coefficient. Now from all these ratios, find which one is the least one, smallest number. It will tell you that it is your limiting reactant, and then proceed simply. After finding the limiting reactant, it's very easy to get the product and the excess reagents. Are we clear? Right? In stoichiometry topic, one more small point is here where students always make mistake. I will call it, what is it? It's percentage purity. Okay, very important, and students always make mistake here. So listen very carefully. Percentage purity. What is it? Pure reactant. We are having here pure reactant divided by impure reactant. Impure reactant you can say, or you can say that it is the reactant you bought from market, and from market you bought the reactant but it have impurities, right? So into 100. So pure reactant which actually do the stoichiometry or do the reaction. Impure reactant into 100. So very simple thing. Let me take one example. It will help you. Sorry. Okay, so what we have now, see carefully. One question I am taking. They are saying how much weight of 60% pure, how much weight of 60% pure CaCO3 will be required to produce, I can say 44.8 liter of CO2 gas, right? Very simple question, very important. Look carefully. First write the reaction. CaCO3 on heating give us CaO2. From the given product, first of all, find the actual reactant required. Then using the percentage purity, we will try to find which one? The impure reactant amount which we are buying from market, right? What do we have? Look at this carefully. Stoichiometry clearly telling us that it's 1 mole, give me 1 mole of CaO and 1 mole of what? CO2, right? So from here, if you see, they are giving 44.8 liter. If you understand carefully, how many moles are there? 2 moles. 44.8 liter at NTP conditions, right? Or STP condition. If they don't mention, by default you will take that, right? So actually I want to have how many moles here? 2 moles. So for 2 moles production, I need its 2 mole, right? 2 mole means how much weight? 2 into what? 100. So how much coming? 200 gram. Now 200 gram is the actual weight which we need here, right? So 200 gram is the actual weight of CaCO3 which we need. But they are asking our reactant which we are buying from the market is 60% pure only. So be careful about it. Look, 60% is the purity. Here 200 gram is the pure reactant. And they are asking us to find the weight of what? Impure reactant. So carefully give the answer here. What is coming? 100. So you find the impure CaCO3 which we are buying from market. So what is coming beta here? How much coming? It goes here 200 into 100 by 60. This will be the weight. And remember, what students do here? They do reverse. They do 60 by 100. No. If 200 is the actual required, then I will buy more from the market, because after removing impurity, I will need 200. I will buy extra, maybe 240, 230, so that after removing impurities, I will get 200 pure. So be careful when you find the final reactant, impure reactant amount. So please 100 by impurity, 100 by purity percentage. Not like 60 by 100, it's 100 by 60. Be careful about it, right? Very important point here. Now, the next thing is, here we are having, it's which one? I am talking about the empirical formula. From here also, nowadays question is coming. Empirical formula, we have to find from what? From the given mass percentage. Like last year they asked question from carbon and hydrogen, right? So simple question we'll take. How to find empirical formula by the percentage weight. Like I'm taking one example. Here are the elements: carbon, hydrogen, oxygen. These three elements are making a compound. They gave the mass percentage. In the compound, the mass percentage of carbon, imagine 4.54% given, hydrogen given 9.09%, and oxygen given 36.36 or 37 almost. They are saying a hydrocarbon made up of carbon, hydrogen, oxygen is containing this percent of elements by mass, and using this mass percentage find the empirical formula, right? What to do? If I imagine I have 100 gram of this given compound, what I will do? So in 100 gram I have 55.54 gram of carbon, 9.09 of hydrogen, and remaining what? Oxygen. So from the given mass percentage find the moles and the molar ratio. Whole number molar ratio, simplest molar ratio give us what? Empirical formula. So nothing, just we have to use the formula weight by molar weight to get the molar ratio, and very easy. So here you look, I have to find moles. How I can find moles here? 54.54 weight divided by how much? 12. 9.09 divided by how much? 1. And 36.37 divided by how much? 1. Right? Sorry, not 1. Oh, 16. You divide it. What's coming here? If you solve it, 4.54 almost, it's coming how much? 9.09, and here almost 2.27. We got these numbers. This is the molar ratio. But the question is this molar ratio is a whole number ratio? No, it is fractions, decimals. So how to make this decimals into molar ratio, right? What we will do? We will do one thing. We will choose smallest number out of these and we will divide all of these by the smallest number, which will help us to convert this point decimal things into whole number, right? I am dividing all of these by smallest number. It's 4.54 divided by 2.27. 9.09 divided by how much? 2.27. 2.27 divided by how much? 2.27. Very good. So very simple thing. How much coming? 2. How much coming? 4. And how much coming? 1. So you can see clearly what is the formula coming. Formula is coming C2H4O1. So it is the empirical formula. It is the empirical formula, right? And if by chance you have to find the molecular formula, then you should know the molecular formula is what? N into empirical formula, right? And molecular weight is what? N into empirical weight. So if by chance they gave you molecular weight, from the empirical formula you can find what? Empirical weight, you have molecular weight, find N. And using N you can convert your empirical formula into what? Molecular formula, right? So very important topic from here, right bache? Good. Now let us see the next point is some concentration terms, right? So what about the concentration terms? It comes in two chapters. One you can say our mole concept, stoichiometry, and one is solutions. In both these chapters it comes, right? There are some terms which are temperature dependent and some are temperature independent, clearly. So we will see the relationship between these terms, okay? Time is little less, so come to the terms. It's concentration terms, right? What do we have here? We can see, first I am writing here temperature dependent, and then here you can take its temperature independent. Any concentration term, any term which include what? Which include volume will be temperature dependent, and any term in which only mass is given, no volume is coming, is temperature independent, right? Why? Because you know that volume depends on temperature. If volume will be affected, then the term will be affected, right? So main things if I take, the first one is you can say weight by volume percentage. The second thing is volume by volume percentage. The next one I can say is molarity, right? And one is which one? Normality. This is normality. And one more you can take which one? Strength. This is your strength. If I go here, it's weight by weight percentage. Second thing you can take here, which one? Mole fraction you can take. It's mole fraction. And the next you can take which one? Molality. It's a molality, right? The formulas you know very well. So I am just saying the formulas. What is weight by volume? Weight of solute in grams, volume of solution in ml into 100. Volume of solution, volume of solute divided by volume of solution into 100. What is molarity? Moles of solute divided by volume of solution in liters. Normality, number of gram equivalents of solute divided by volume of solution in liters. What is strength? Strength is, carefully, weight of solute. Strength is weight of solute divided by volume of solution in liters. How it is different from molarity? Molarity have number of moles of solute. If I say in short, molarity is number of solutes, number of mole of solute divided by volume. Strength is weight of solute divided by volume. So there is a difference, right? Be careful about it. But volume is coming in both, so both are temperature dependent. What is weight by weight? Weight of solute divided by weight of solution into 100. Mole fraction, mole of that component divided by total moles. And the sum of the mole fractions of all the components are equal to what? 1. Very good. Molality, number of moles of solute divided by weight of solvent in kg, right? The terms and the formulas you can see in NCERT also. Now the relationship is very important here, right? So I am writing some relationship. First relation I am writing here, look at this. I can say the mole fraction and the molality. The formula is 55.5 x 1 minus x. X is the mole fraction of solute, right? This way you can get from mole fraction to molarity very easily, right? The second thing, if I say, you can take molarity. Molarity is 10 into weight by volume percentage divided by molar mass of solute, right? The second short formula. If I say third one, you can say molarity is what? 10 into weight by weight percentage divided by molar mass of what? Solute, right? And here one extra thing is coming, density of solution. See carefully, there is a difference. It is weight by volume, so no density required here. It is what? Weight by weight, so I need density of solution. These are very important formulas. Many times it comes in use, right? And the next thing, if I say relation between the molality with molarity, so 1000 into molarity divided by 1000 into density of solution minus molarity into molar mass of solute, right? Easy? Clear? Okay, right. And the next one, sometimes students remain confused in the normality terms. So please, if you are confused in normality by chance, you become gajani and you forgot everything. So you first just find the molarity, because molarity is more simple to find, and then use n factor to find what? Normality, right? So what is normality? Normality is n factor of solute into what? Molarity. So these are some short relationship between these and the temperature dependence, or you can say temperature independent, right? I am giving a small question, so please try to find it. Now I am saying find mole fraction. Find mole fraction of NaOH in 10% weight by weight NaOH solution, right? This is a question. So they are relating weight by weight percentage with what? Mole fraction, right? What we have? What is the meaning of this thing? It means they are trying to say 100 gram solution. They are trying to say 100 gram solution have 10 gram what? NH. And they are saying 90 gram what? Water. Okay? It means 100 gram solution have 10 gram NaOH and 90 gram what? Water. So easy to find the mole fraction of NaOH, right? How we can find? Moles of NaOH 10 by 40 divided by 10 by 40 plus 90 by how much? 18, right? So what's coming here? 0.25 divided by 5.25, which is giving us almost 1 by 21. Fine. This way you can relate them and you can get the answer also. Fine. Okay, this is it about your first chapter. Now let us move to the second one, that is your atomic structure, right? Structure of atom you can say, or we can say atomic structure, right? So the chapter starts with the you can say discovery of fundamental particles, that is electron, proton and neutron, right? So their discoveries are discussed, how they found the electron, proton and neutron. They gave the scientist name also. And after discovery of fundamental particles, then they come to the atomic models, where these electrons, protons and neutrons are present in the atom. Like Thomson gave Thomson plum pudding model, water melon model. Okay, he said atom is like a watermelon, in which we have a positive charge sphere in which electrons are present like seeds. Okay, the only one good point was that he said atom is neutral. That is the only right point. Remaining points were the wrong. Then which model came? Rutherford model, right? Rutherford model was a big success. He only tells us that atom is having nucleus. Nucleus discovery is given by what? This credit goes to Rutherford. He said center of atom is small and it contains positive charge and most of the mass of the atom, and electrons revolve around the nucleus. In the outer shell we can call it extranuclear part. He said proton and neutron are present in the nucleus, and that's why we call them what? Nucleons, right? So Rutherford definitely gave a very good model. One or two limitations were there, like he was not able to explain what? The stability of atom, right? Because according to classical physics, accelerating charged particles should lose energy and it should fall to the nucleus. But Rutherford was not able to explain that part. So in between the Rutherford model and the Bohr model, which was again a big success, some points came. One of the point was which one? Maxwell's EM wave theory and Planck's quantum theory, right? So we can see here some points I am taking, like in the Maxwell's EM, electromagnetic wave theory, less chances to ask direct question here. Look at this first. He gave this point that every electromagnetic radiation have some fixed characteristics, like electric field and magnetic field will associate with every EM wave. Second, he said every EM wave travel with what? Speed of light. Next point, he said there is no need of materialistic medium. EM waves even can travel in vacuum, right? And the formula, the two formulas are, first one was C equals to nu lambda. You can use it for every EM wave. And the next one was wave number is equals to what? 1 by lambda. And the most important thing from NEET point of view here is the electromagnetic spectrum. That's why I am discussing this topic. It was electromagnetic spectrum. Many times they ask this question, that if you see here carefully, it is C, G, X, UV, V, I, M, R. What are these things? What I am writing here, you see carefully. C means cosmic, cosmic rays. G means I am saying gamma. X means X-rays. U means what? Ultraviolet rays. V means which one? Visible I am talking about, visible. I means infrared. M means microwaves. And R means radio. So this sequence is very important. So from here to here, if you go from here to here, you see the lambda value is increasing. The wavelength of radio waves is largest. The wavelength of radio waves is largest. Whereas if I say, if lambda increase, frequency decrease, wave number also decrease, and the energy of photon related to this radiation will also decrease, right? This is the sequence. This sequence is very much important from this theory. And this Maxwell's theory, James Maxwell explained the wave behavior of radiations. He explained the wave behavior of radiations, right? Now but it was not able to explain many phenomena like photoelectric effect and black body radiations, right? Because these topics or these phenomena are depending on the particle nature of radiation. Then who came? Then next one was Planck's quantum theory, which is very much important. Okay. So Planck's quantum theory. Planck's quantum theory said that the EM waves or radiations have both the behavior, like wave behavior definitely Maxwell explained, and Planck's quantum theory explained it have particle behavior also, right? Radiations particle behavior explained by Planck's quantum theory. And he said very two important points. He said energy absorption or energy emission from a body is always a discontinuous phenomena. It's a discontinuous phenomena. If I am losing energy or someone losing anything, even black body, sun, if anything is losing energy or absorbing energy, it will do this in a discontinuous phenomena in form of energy packets. We call them what? Photons. We call them photons. And the energy of photon is proportional to what? Frequency. So I can say that energy of one photon is equals to what? H nu, where H is what? Planck's constant. And if I want to find total energy, I will say NH nu. What is N here? N is number of photons. If I am absorbing 5 photons, so I will absorb 5 into H into nu. If I am absorbing 1 photon, I will absorb how much only? H into nu. Right? Clear, bache? So this is how you can relate it. I am saying once again, it explained the particle behavior of radiations or light and gave 2 points. Emission of energy or absorption is always discontinuous, and energy of photon is proportional to frequency. From that we can write these 2 formulas, right? Like if I ask you simple question, one question I am asking, find total energy of 2 moles of photons, 2 moles of photons having frequency 10 to the power how much? 10 hertz, right? So it's very easy. I am finding ET, total how much photons? 2 moles beta, 2 into Na. Na means what? Avogadro number. So many photons I have. H nu, what is H? 6.6, 10 to the power how much? Minus 34. Nu 10 to the power 10. This much energy will be absorbed by something if it absorbed 2 mole of photons. Remember, N is not number of mole here, N is number of photons. So 2 mole of photons means 2 into Na photons, right? This is it about your Planck's quantum theory. Now Bohr used these 2 points and gave his model, you can say Bohr's atomic model, the very important, most important model, right? So we can see here Bohr's atomic model. What do we have here? Bohr's atomic model. So first of all, he gave some postulates. What he said? He said electrons will revolve in some stationary paths around the nucleus, and electron will not lose or gain any energy when it is revolving in its shell. I am saying once again, electron will not lose any energy or will not gain any energy if it is revolving in its shell, if we are not disturbing it from outside. It will continue revolving in the same shell for complete of its life if we are not disturbing it, right? So it will not fall in the nucleus or it will not lose any energy, right? Second thing, he said the paths, stationary paths where electrons are revolving, We can call them stationary paths first of all, then you can say shell, or then you can say orbits. So any of these is fine. He said energy of electrons are quantized, means energy of electron can have only some fixed values. It can't have any some random value. Some fixed values are there, and out of these values electron will have some of this part, right? Like I have 500 rupees note, so I can give you 500 or 1000 or 1500 or 2000 or 2500. So we have a fixed value now. We can't have any value, right? The next thing, if you see, the next thing he said, the angular momentum of electron is quantized. He gave the formula mvr equals to nh by 2 pi. It can be 1h by 2 pi, 2h by 2 pi, 3h by 2 pi. So energy as well as angular momentum of electron is quantized. So these are some postulates, right, about the Bohr model. And then the features, if we talk about, right? So what are the features? The first point, if I say about the feature, you can talk about energy. This model is applicable only for one electron system. If I say you can apply this only when is it hydrogen or helium plus or lithium 2 plus or beryllium 3 plus. Otherwise you can't apply it. Only one electron system. The formula is very much important. Which one? Energy. If I want to find energy in a particular shell, in a particular atom, what is the formula? Minus 13.6. What's coming here? Z square by n square. Electron volt per atom, right? Electron volt per atom. Fine. Now, if I go for the radius formula, it is 52.9 n square by z. It's in picometer. Okay. Now, if I want to find the velocity of a particular electron in some particular shell, so I can say it is which one? You can say 2.18 10 to power 6 z by n meter per second. Units are very important. Okay, units are very important. Next thing, if I say fourth one, the angular momentum. So we discussed about it. mvr equals to what? nh by 2 pi. So these are two formulas: energy, radius, velocity, and angular momentum. Some extra points are there. We will discuss about it. First of all, let us see. Okay, we can take the next slide. Okay. So the next one, if you see, bache, like imagine I'm asking, I'm saying some example. I am finding the energy in helium plus third shell. I want to find the energy of a third shell of helium plus ion. For helium, what is Z value? 2, right? Apply the formula. Minus 13.6. Z square by n square. Z square by what? N square, right? Means I can say 3 square. In which units? Electron volt. Clear? Imagine I want to find radius of lithium 2 plus, and I'm saying it is a third shell, right? Third shell. What is the formula? 52.9 n square. N square by Z. Z is what for lithium? 3. In which units? Picometer. And if I am saying, please find the velocity. Find the velocity of which atom? I am saying in hydrogen atom's fourth shell. So I will apply a formula 2.18 10 to power 6. Z by n 1 and Z by n beta. Which one n? Fourth meter per second. So very many times they ask this question. Simple question, right? What is the point? This is it. Now, some important points which NEET ask many times. First of all, if you see, I am taking about, this is the nucleus imagine, first shell, second shell, third shell, fourth shell. If you apply the formula and you find the energy, what's coming here? If you find energy, it's minus 13.6, right? If you find here, next one is coming how much? almost minus 3.4. Okay, next if you go over it's 1.51, or next if you go minus 0.85, right? You can apply the formula to get the points easily. You see, energy is increasing. If I compare E1, E2, E3, E4, energy is increasing because that infinite shell, in the infinite shell, energy is what? 0. That's why when an electron comes closer to the nucleus, energy release. As I am taking 0 at the infinite shell, so it is most negative near what? Near the nucleus, and that's why we call it the minimum. As shell number increase, energy increase. So carefully, what question they ask many times, if I compare E1, E2, E3 and E infinite, which one is high beta? Energy increase. Similarly, if you compare radius R1, R2, R3, definitely it increase, and maximum where? At R infinite. So energy and radius will increase as shell number is increasing. Fine. Next thing, the velocity. Here some unexpected thing you see, V2, V3, and here you can say V infinite. So velocity decrease. As shell number increase, the velocity decrease, means electron will revolve more fast in the first shell to balance the electrostatic forces between the nucleus and the electron, right? So here you see it is Z by N, more the N lesser the what? Velocity. More the N lesser the velocity. Fine bacha, clear? Now if you look at the next part, it's about the velocity. Now the next thing is, from where NEET always asks questions, if I compare the E2 minus E1, this gap, if I go further, E3 minus E2, this gap, and if you go further, E4 minus E3, this gap it always decrease. Energy is increasing in higher shells, but the energy gap between the first and second shell is very high. The energy gap in third and second is less, and 4 and third is more or less. So energy gaps is decreasing. But if I talk about the radius, look carefully. It is the gap of R2, R1. Now gap of, I am saying here which one? R3, R2. And now gap of, imagine R4, R3. This gap is increasing. The energy gap is decreasing, but the radius gap is increasing. You can apply the formula to check this easily. Okay, got the point? These are very, very important points, theoretical points I will say, which NEET always ask. They gave some statement questions, assertion, reason. They can ask these things very clearly, right? Easy part. Now this is it. And the next thing, if I say, imagine they ask sometime they gave energy of one shell and they ask energy of some other shell. Just apply the formula Z1 square by N1 square divided by what? Z2 square by N2 square. Similarly, radius, they gave one of the radius and they asked other radius in terms of first one. So what is coming here? N1 square by Z1, N2 square by Z2. And the next one is V1 by V2, that is which one? Z1 by N1, and here Z2 by N2. Fine. When to use these formulas? When they give these atoms, this shell have this energy. To find this atoms, this shell's energy. So one is given, one they are asking in form of other. They give radius of this atom, this shell is this much. To find the radius of this atom, this shell. So they will ask one thing in form of other. So always go in ratio form. It will be saving time for you. Okay. This is it about your Bohr model. Very, very important. The next thing is the limitation of Bohr. It can't explain the Zeeman effect, splitting of spectral lines in magnetic field. It can't explain Stark effect. It can't explain spectra of multi-electron atoms. Many things are there, right? And now I am going for the hydrogen spectra, right? So I am coming here only. In hydrogen spectra, there are two things are very important. right? So I am discussing about hydrogen spectra. Bohr model was able to explain the hydrogen spectra. In hydrogen spectra, there are two types of questions basically, two formulas only. And you see the first one. First one is number of maximum possible spectral lines. The first formula is number of maximum possible spectral lines, right? What is the formula beta here if you see? N2 minus N1 plus 1 into N2 minus N1 divided by what? 2. This is the formula to find the maximum number of possible spectral lines. If electron jumping from some higher shell to lower shell, so how many lines, different type of lines, or I will say different type of photons it will emit, or I will say it can emit, right? Like if I take example here, what do we have? First example I am taking, imagine question is find maximum possible spectral lines in electron transition from, I am saying, 6th shell to first shell, right? To first you can write, or maybe second they can give, or whatever they give. N2 I have 6, N1 I have how much? 1. So we can apply the formula N2 minus N1 plus 1 into N2 minus N1 divided by how much? 2. What's coming here? 6 into how much? 5 divided by 2. So 2 give us 3. So how many coming? 15. So total 15 lines will come. Or I can say total 15 type of photons it will emit. 15 different type of photons. Maybe jumping from 6 to 5, 5 to 4, 4 to 3, 3 to 1, or directly 6 to 1, maybe directly 6 to 2, then 2 to 1. So different types of lines can come, so many, 15. Or different type of photons can emit, right? That's it. Second question from the hydrogen spectra is they will give properly for this line, electron is jumping from here to here, this shell to this shell, and when this jump happens, energy will emit out or radiations comes out. So you have to find the wavelength or wave number of that particular wave, or can you say radiation, like I am saying. So find wavelength. Find wavelength of radiation emitted. Find wavelength of radiation emitted in electron transition from where to where? From you can say 5th shell to first shell. Here they are saying electron jump directly from what? 5th to 1st. So I can talk about this one. What is it? 1 by lambda, the formula 1 by lambda. What do we have here? R, Rydberg constant, 1 by 1 square minus what? 1 by 5 square. That's it. If you solve it, what is coming? 1 by lambda. R is coming here 21 by, 21 by how much? 25, right? 5, here 5, how much coming? 5 here, 25, 24 by 25, right? If you solve this thing, so lambda is coming how much? 25 by 24 R. Fine. This way you can solve it very easily. Clear? The two formulas are there for the, what is the formula exactly? I will say 1 by lambda or wave number equals to R. 1 by n1 square minus 1 by n2 square, right? If n1 or electron is coming to the first shell, we call this line belongs to Lyman series. If it comes to second shell, Balmer, third shell, Paschen, fourth shell, bracket, and if it comes to fifth shell, it is which one? P-Fund series. So sometimes they will say electron jumping from 8th shell and it belongs to Balmer series. It means coming from 8, means N2 is 8, and Balmer series means N1 is what? 2. Coming from 10th shell and it is part of P-Fund series. It means coming from 10th shell, and P-Fund series means coming into 5th shell. So you can apply a formula simply to get the answer, right? Clear? So this is it about your hydrogen spectra, right? Now the next thing, if you go, is quantum numbers. So quantum numbers, if you see, after the Bohr model, then Erwin Schrödinger and Heisenberg gave the quantum mechanical model of atom, where they said clearly that it is not possible to find the exact position of electron. So they bet on the probability. The reason where electron finding chances are more, we call it orbital, and where electron finding chances are minimum or negligible, we call it node, right? So psi square gives us the electron probability density at some point. Psi square, psi, it comes from Schrödinger wave equation. And the main thing which that model gives us is quantum numbers. There are 4 quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and which one? Spin quantum number, right? So what N tells us? N gives us the shell number. It gives us information about shell number. L gives us information about subshell number. M gives us information about orbital number, and it gives us spin of electron. Spin of electron, right? Means it have only 2 values. Which one? Plus half, or which one? Minus half. So 3 quantum numbers are enough to give you the position, or I will say the designation of electron. S is not telling about the designation, it is just telling the spin. Our electron is present where? 3 are enough: N, L and M, shell, subshell and orbital. S is not telling about the position or the designation of it, right? Instead of this, N give us what? N give us you can say size and energy of orbital. Size and energy of orbital is given by N. L mainly give us the shape of orbital, right? M give us what? Orientation of orbital. Right? S to give us only what? Spin. It gives us only spin. So shell, subshell, orbital. L value, if you see carefully, L value depends on which value? N. From where to where? 0 to N minus 1. So in which shell, how many subshells can exist? It depends on the N value. L values will come from where? N. And M value come from where? From the L. So M is possible like minus L to what? Plus L. So in a shell, how many subshell exist? It depends on the N value. In a subshell, how many orbitals can exist? Depends on the L value, right? You know this very well. Clear? Good. So the main thing I am saying once again, many times they ask. So N give us size and energy of orbital. L give us shape of orbital, and yes, also contribute in energy also, because sometimes N plus L decide energy, right? And M give us orientation of orbital. Orientation means electrons are oriented in which direction? Maybe X direction, Px, Py, Pz, or Dxy, Dxz, Dz square. So where electrons are oriented, right? This will give us that information, right? The next thing, if we talk about is next one, like very important expected question, which set of quantum number is not possible, or I will say which set of quantum number is not possible, right? So we can say here, I am saying this is N here, this is L here, this is M here, this is S. So first one, 3, 2, 0, minus half. Second I am saying 4, 3, 2, plus half. And third one is 4, 4, 2, plus half. And if I am saying fourth one, like I am saying 3, 0, 0, minus half. So which one of these not possible? Very commonly this question comes in the NEET exam. So if you see carefully, third option, if n is 4, what can be L? It can be 0, it can be 1, it can be 2, it can be 3. But L value can never be 4 or equals to n value. That's why it don't exist. So these questions are very common to be asked in the NEET exam, right? Then it comes that compare the energy of following orbitals. So I am giving one question over here. Compare. If I say energy comparison between orbitals, right? So we have here energy comparison between orbitals. So what they are saying, imagine I am saying here, first of all, n plus L decide. Higher the n plus L, higher the energy of orbital. If n plus L tie, then go for n. Higher the n value, higher the energy, right? If I take one example, look, we are having 3s, we are having 4p, we are having here 5d, and I am saying here we are having 4f. I want to compare energy of these 4 orbitals, and I am saying it's a multi-electron atom. In single electron system like hydrogen or helium plus, only n can decide energy. Higher the n, higher the energy. But in case of multi-electron, n plus L will decide first. If n plus L is tie, then who will decide only? N will decide, right? So in this case, you see, what is the n plus L value? 3 plus how much? 0. 4 plus how much? 1. 5 plus how much? 2. And 4 plus 3 how much? 7. Right? So if we compare energy beta, so which one has the minimum n plus L value? You can say 3s. Then which one? 4p. Right? Next which one? 5d and 4f. 5d and you see 4f. Both have how much n plus L value? 7. So if n plus L is same, then who will decide energy level? N will decide, right? So after 4p, I will go for which one? 4f, right? Then which one? 5d, right? I am saying once again, n is 5 and d is what? 2 for this. N is 4 and f means what? L value, 3 value, right? When both are 7, 7, then I will use the n rule. N, higher the what? Energy. Clear? What is the point? This way we can compare. Now the next thing is our next chapter I will take. Okay, and one more thing I will say. When we fill the electrons in these orbitals, we will use 3 rules: Bohr rules, Hund's rule, and Pauli's rule, right? Hund's rule say that we should fill the electrons in increasing order of energy in the orbitals. Hund's say if electrons, you are filling electrons in degenerate orbitals, then fill first single electron and then you should start the pair. And Pauli rules say that you should only max to max you can fill 2 electrons in orbital, and both electrons should be what? In opposite orientation. Okay, So one small question I want to ask you, like chromium. I want to ask chromium. I'm asking the chromium configuration. Chromium configuration is like 24. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. If you look here carefully in the last one, 4s1, 3d5, you have to just answer me that it is breaking which rule out of 3 rules? 4s1, 3d5, sorry. It's 4s1 and 3d5. It is breaking which rule? It is violating Bohr rule. Why? Can you answer this question? It is violating Bohr rule. How? Because we are filling the higher energy orbital instead of completely filling which one? Completely filling the lower energy orbital. I am taking its one electron here. Right? That's why we are making mistake, or I am saying we are violating which rule? Bohr. Actually, I should fill this full. Then I should go for next one, right? But here, we are filling it half only and jumping to next shell. This is Bohr rule, very important rule, right? This is it. Now let us come to the next one, that is thermodynamics, and we will see what are the important points here. Fine, bache? Okay. It's thermodynamics, right? So we'll see. We'll start from some basic terms in thermodynamics. I'm using we can use little NCERT also here. So just simple terms you can tell me. Okay, first tell me what is system. System is a thing about which I am talking. System are of 3 types, right? System are of 3 types. One is open system. Open system is that system where you can exchange energy as well as matter to the surrounding. Whereas closed system is that system which can exchange only energy, but it can't exchange matter with the surrounding, right? And the next one, if I say, it is which one? Isolated system. Okay? So isolated system can't exchange energy as well as matter with the surrounding. Fine? Open system can exchange both energy and matter. Closed system can exchange only energy, and isolated system can neither exchange energy nor matter. Very simple thing, right? Now the next thing is, there are 2 types of functions. Some are state functions, some are path function. State functions are those functions the value of which depends on the state in which our system is present. Its value do not depend by which path you have attained this state. We call them state functions, like you can say enthalpy, Gibbs free energy, pressure, volume, temperature. These terms don't care from which path you have attained the state, right? Whereas 2 functions are there which depends on the path. Or I can say you can discuss about these functions only when you are going one state to other state. You are going through a path, like heat and work. Heat and work are path functions. Remaining all, whatever comes in your syllabus, you will say state function. Only heat and work are path function. Even in some conditions, this heat and work can also do cheating. But if they are not giving any condition, then heat and work is path functions. Otherwise, remaining are state functions, right? Clear? Heat and work depend on the path you are taking to go from state 1 to state 2. But the remaining thing, delta H, delta U, delta G, delta S, their values do not depend on the path taken to go from state 1 to state 2, or their values do not depend by which path you are changing your state, right? Now If we discuss about the type of processes, like I will come to the right. So last in the NEET exam they asked one very important point. If I ask you what is the meaning of isothermal process, tell me better. What is the meaning of isothermal process? The process in which temperature remains what? Constant. Or I can say delta T is what? 0. In the whole process, temperature is not changing. Or I will say delta T is 0. We call them isothermal process. Second thing is isochoric, you can say. Isochoric process. It's a question of last year, beta. Isochoric process, where V is constant, means you are not changing the volume during the process. So delta V I can say is how much? 0. The third I can say, you can talk about which one? Isobaric process. Third one is isobaric process. In isobaric process, you see pressure remains constant, no change in pressure during the process. So delta P is 0. And next I can say very important, adiabatic. In adiabatic process, you say no heat exchange. I will not say heat remain constant. I will say no heat exchange. That means Q is 0. We don't write delta Q is 0. We just say Q is 0. Be careful about it. It's a path function and we don't put the delta word here. No heat exchange means Q is 0. Actually, heat can be discussed only when there is exchange. Heat does not mean that this substance has this much heat. No, it does not make sense. During this process, how much heat is exchanged? That is Q only. So instead of saying delta Q, I will say just Q. Or I will say no heat exchange. What is the meaning of cyclic process? Cyclic process means when final conditions and initial condition are same. You are traveling through a path, but you are coming to the same state finally as of initial state. We call the cyclic process. In cyclic process, every state function value, change value, I will say change, will be 0. But path function will be non-zero. Like if I am going from here to here, delta U, delta H, delta G, everything is 0. But work done is not 0. Okay? Heat change is not 0. Right? And if I say one is known as reversible process and one is known as irreversible process. One is irreversible and one is reversible. Reversible process can proceed in both directions, forward as well as backward. It will be very slow process, it will take infinite time to finish, right? And reversible and irreversible, I will say, sorry, irreversible is next one, which will be very fast, will move in only one direction, okay? And in irreversible, you see P external will be very far higher or very lesser than the P external. Means P external, P internal will not be close, high difference. In reversible process, P external and P internal will be very close, right? Their value will be very close. That's why the process can stay at equilibrium, or I can say the process will remain what? Reversible, right? The next thing, I'll come to the first law of thermodynamics. What this law say? According to this law, the energy can neither be created nor can be destroyed. It can just transform from one form to another, right? And the mathematical expression for the first law is which one? Delta U is what? Q plus W. Delta U is change in internal energy. Q is Q is what? Heat exchange, and W is what? Work, right? So if I say Q, if our system is absorbing heat, heat absorption will be positive because it will increase the delta U, internal energy of system, whereas heat released will be taken as negative when we are finding delta U, and work done by system will be taken as negative because it will cause decrease in internal energy, and work done on system will be taken as what? Positive, because it will increase the internal energy of system, right? So let us see. Very important question from the NEET exam. Simple example I am taking. This is your system. This is our system. I am saying work done by system, and I am giving the value. How much value? 800 joule. And here heat absorbed by system, and I am saying the value is 1000 joule. They are asking find the delta U. So how you will find? Delta U is what? Q plus W, right? So what is Q here? Q, I should take positive or negative? Absorbed. So it will give you 1000 joule. Positive. It is increasing the internal energy of system, right? And plus how much? Plus work. What is work? Minus 800. Because system is doing work. If system is doing work, it will cause decrease in its internal energy. So I will take minus. Total how much coming? 200 joule. Very important. NEET asked it last year, right? It's a very simple question. Heat absorbed, positive, released, negative. Work done on system, positive. Work done by system is what? Negative, right? Clear? So be careful about it. Now, here the work was simply given in this question, but sometime we have to find the work. In such cases, if I talk about the work, look carefully, work. So two formulas of work are very, very important. First, if I talk about, if I am saying first is isothermal irreversible, right? Isothermal irreversible. So how much you will find the work? It's a minus of P external into what? Delta V. Very, very important. Minus of P external delta V. Why I am using minus sign? Just so that our formula will work with our sign convention. You just put the formula, convention thinks formula will see itself. So minus P external delta V. P external is outside pressure of piston pressure or atmosphere pressure, whatever they say. It is not the gas pressure, it is external pressure, right? Clear? So it's minus of P external delta V, right? The next thing if I say is this one. B part you can say, it is reversible isothermal. It's reversible isothermal. What is that? Minus of 2.303 nRT log what? V2 by V1. Sometime we can modify this formula also, that this nRT can be taken as PV and this V2 by V1 can be taken as what? P1 by P2, right? PV, it can be P1 V1 or P2 V2 because both will be same in case of isothermal process, right? So be careful about it. Clear? So the next thing, I am taking one example here. Carefully answer me. Find work done. Find work done if gas expands if gas expands from 2 liter to 10 liter, you see what they are saying, against a constant external pressure of 5 atm. When they mentioned against a constant external pressure of 5 atm, that means they are telling us this is a irreversible process, right? So what we have to do? What's work here? Apply the work formula, minus P external. What is that? 5 delta V, V2 minus V1. What's coming here? If you see, minus 40 atm liter, but they will ask in joules, so minus 40 into 101.3 joule. Here we are converting atm liter into joule, that is 101.3 joule. Be careful, they will ask in joules. Most of the time they ask answer in joules, but they give pressure in atm and volume in liters. So don't forget to convert it, because they will give first option as minus 40 joule and you will tick that answer. So be careful about the units. Every year students are making 2-3 mistakes because of units only. And you know, one question costs you how much? 5 marks, and 5 marks can change your college, or if you are on the verge, your selection will be gone because of one question. So be careful about units, especially. Read the question carefully from first point to the last point. Don't just interpret. Sometimes what we do, we start the question by the first line, we think, okay, this is the question, we start solving. No. Read the question completely from first point to the last point, then start doing it. Then make it fast. But you should be clear what you are finding in your question, right? That's it about your work done. Now, next thing, one of the very important point in thermodynamics is your Hess law. I am talking about the Hess law, right? What does this say? Okay, before Hess law, we can discuss little other point also. Delta H and delta U relationship. Again, a very important point from NEET point of view. Every year they ask. Thermo give you 2 questions. These 2 questions can be from work done. This can be from delta H, delta U relationship, otherwise delta G. Okay, so these 3-4 topics are fixed from where they always ask questions. So you can say delta H equals to delta U, and you can say delta PV also. We can make it P delta V if P is constant. We can make it V delta P if V is constant. Otherwise, especially for the reactions, which NEET always asks, for the reactions or phase changes. For the reactions or phase change, this is the very important formula, that delta H equals to what? Delta U plus what? Delta NGRT. Right? What is delta Ng here? Delta Ng is number of gaseous products. Number of gaseous products minus what? Number of gaseous reactants. It is delta Ng. Right? They can ask numerical from here also, and they can ask questions like which of these is higher or lower. When question comes, then which one is higher, delta H is higher or delta U is higher, then please don't look at the sign even. What I am trying to say here, you just go by this way. If delta Ng is coming more than 0 or positive, you can say delta H is more than delta U. If they say delta Ng is less than 0, you can say delta H is less than over delta U. And if they are saying delta Ng is equals to 0, no doubt delta H equals to what? delta U. Okay, but when they ask about the magnitude, especially when they say compare the magnitude of delta H, delta U, then only you solve the question to check their values. Otherwise, they are not giving values and they are just asking that which is larger without giving values. Then you just apply this one. Higher the delta Ng or delta Ng positive means delta H more than 0, delta Ng negative, delta H less than delta U, sorry, and delta H 0 means delta H equals to a delta H. Right? Clear? Imagine if I am saying some example. Imagine I am saying burning of CH4. We are doing combustion, CH4 plus O2 give us what? CO2. So in this case, if I am saying here, if you balance it, what is coming? Sorry, here H2. Right? What is coming here? 2. What is coming here? 2. It's a gas. It's a gas. It's a gas. It's what? Liquid. So I can say from here that delta Ng is what? Delta Ng is negative because 1 gas mole, 3 gas mole, delta Ng is negative. So I can say which case it is. Delta Ng negative means delta H is less than what? Delta U. But if they ask about the magnitude, then you have to solve it properly. In such questions, they should give the values also. Otherwise, if they are not giving any value, they are just comparing delta S, delta U, then don't use extra mind, then apply just simple relationship. If they ask compare the magnitude especially, then you go for the values. Otherwise, apply this one only, right? Clear? Very easy to find. Okay. Right. Next thing, if I say, I can take one example here, like this one. If I am saying reaction is A plus B is giving us 3C. It's a gas here, it's a gas here, it's a gas, right? And I am saying the delta H value is 100 kilojoule. Question is simple, find delta U, right? What I will do here, delta H 100 kilojoule, okay, fine. Delta U I have to find. Delta Ng how much? 3 gas mole, 2 gas mole, 1. Delta Ng 1. RT, what is RT? R 25 by 3 10 to the power minus 3. I am taking R in kilojoules, right? And T imagine given as 27 degrees Celsius. So how much will come from here? 300, right? The temperature here how much? 300. Clear? So you can just put the values here, the answer from here. If I am saying it is 100 coming, delta U coming, plus this will cut it down. How much coming? 100. How much coming from here? 2.5 will come, right? If you solve it. So delta U is coming how much? 97.5 kilojoule. Okay, this way you can solve it. Use the R properly. Don't put some random units of R. If you are using energy in joules, take 25 by 3, 8.314. If you are using kilojoules, then use 25 by 3 into 10 to the power minus 3. If you are using other units, so use R accordingly. Clear, bache? Right? Now, the next thing is about the Hess law. Again, very important. Hess law, right? What is Hess law? We know that the delta H, if I say delta H is extensive property. It is extensive property, definitely depends on what? Depends on the amount taken. And the second thing, if I say it's a state function, we know that it is state function, right? So if I'm going from A to B by direct path, I'm going from A to B direct path, I'm saying delta H dash. Or I'm going A to C, C to D, D to E, and then E to what? B. So in this path delta H1, in this path delta H2, in this path delta H3, in this path delta H4, right? So if you go from here to here, we'll see beta what will happen. So I can say the delta H dash is equals to what? Delta H1 plus delta H2 plus delta H3 plus what? Delta H4. What is this? How I can say this? Because it is a state function. Enthalpy change will not depend on the path, what path you are choosing, what path you are taking, right? If you go by the direct path or if you go by some other path, the delta H value will come what? Same. Because of this property only, I am able to write this. Clear? So if I'm writing a question here, imagine A to B, the delta H value I am saying it is X, imagine, and I am saying here it is B to C, or I am writing something else. I am saying imagine C to D, right? And here the delta H value how much? Y. By using these two equations, I want to find this one. I want to find 2A and I am saying 3D is making 2B and 3C. Using the above two equations, I want to make third equation and I want to find what? Its delta H dash. I want to find its delta H dash. Clear? So how we can do this? First of all, there are three principles to solve this thing. First one is what I need. Second thing, how much I need, and third thing, on which side I need, right? So look at the first one. What I need A. Where is A? A is present in the first equation. What is A? A is present in the first equation, right? So I will use first equation to get A. But I need 2A, but here how much only? 1A. So I will multiply by what? 2. I will multiply by 2. Side, left side, here also be side, left side. So I will not flip, no need of flip, left. So just use it as 2 of delta H1, right? Next thing, I need D. Where is D? D is present in second equation. How much I need? 3D, but here only how much? 1D. So multiply 3 into delta H2. Second thing is, I need on which side? I need on left side. But where they gave? They gave on right side, I need left side. So what is important? Flipping. I will do flipping. Flipping gives us what? Minus. So I can say that the delta H dash equals to how much? Delta H1 minus 3 delta H2. Delta H1 minus 3 delta H2. So what is delta H1 value? I can say X minus 3 into what? Y. So what is coming finally? X minus 3y. X minus 3y. Got the point, right? Okay. Now after this, if you see the NCERT, they are discussing about different type of enthalpies. Enthalpy of evaporation, enthalpy of sublimation, enthalpy of fusion, enthalpy of formation, enthalpy of neutralization, many enthalpies are there, right? So you should be clear that if I am taking one example, enthalpy of sublimation. So I am converting 1 mole of given solid into 1 mole of gas. 1 mole I am saying, right? It is for per mole. If I am talking about enthalpy of formation, so I will make 1 mole of the compound from the simplest of its constituents in their standard state. Enthalpy of combustion means I will burn 1 mole of the given compound with the help of O2 and whatever it makes. Right? Clear? So don't forget, you have to take 1 mole. If I am saying enthalpy of neutralization, so acid and base will neutralize each other and will form 1 mole of water. Don't forget, when you write the equation, you have to form 1 mole, or you have to burn 1 mole, or you have to vaporize 1 mole, depending on definition, whatever they're giving, right? One thing I will write here, very important. Imagine if they are giving me a reaction, like we have a reaction here, it's A here, A, imagine B here, some equation coming, C, and giving us D, right? This is the equation. Now sometime they ask us the delta H of reaction, and they give us different things. Sometimes they say in the question what is given, enthalpy of formation of A is given, formation of B, formation of C, formation of D. If they have given enthalpy of formation of everything present in the equation, what I will apply? Summation of enthalpy of formation of products minus summation of enthalpy of what? Formation of reactants, right? Imagine in the question they give enthalpy of combustion of everything A, B, C, D. What I will use? I will use summation of enthalpy of combustion of reactants minus summation of enthalpy of combustion of what? Products. If they give us bond energies of everything, so I will say summation of bond energy of reactants minus summation of bond energy of what? Products. Very, very, very important. It saves a lot of your time. Depending on, for every component what they are giving, use the formulas accordingly. In terms of formation, product minus reactant; in form of combustion, reactant minus product; in terms of bond energy, reactant minus product. From this NEET asked 2-3 times question, and one question was repeated, if you remember, x2 plus y2 makes xy. Delta H of reaction was given and they were asking the bond energy of xx, right? So very, very important, use it properly, right? Okay, this is it. Now a small thing I will say about spontaneity. How you can predict spontaneity properly. Who can predict spontaneity? First of all, delta S total can predict spontaneity without exception. Delta S positive, spontaneous, no doubt. Delta S negative, non-spontaneous, right? And delta S 0, equilibrium. Delta S total can predict spontaneity without, delta S can predict spontaneity without exception. Total, remember total. Delta S system alone or delta S surrounding alone can't decide spontaneity. But the issue is to find delta S total, I need delta S of system also, surrounding also, little tough. That's why we try to find delta G system. If delta G system is negative, then you can say process is spontaneous. If delta G system is what? Positive, you can say it is what? Non-spontaneous. And if delta G system is 0, you can say what? Equilibrium, right? You can say equilibrium. Fine, clear? So delta G system can find spontaneity or delta S total can find spontaneity, right? Alone delta S system, delta S surrounding, delta H system, these things can't find spontaneity alone. But these alone can find what? Spontaneity. Be careful about it. And if you want to find delta G system, how you can find? You can use the formula, the delta H system minus what? T delta S system. So these two things can help you to find spontaneity. But alone these can't decide spontaneity. Together they can decide using what? Temperature. Very common question they ask. In a process, delta S total, so delta S system is positive, delta H system is negative, so it is always spontaneous. In a process, delta H system is positive and delta S system is negative, always non-spontaneous. And other two processes always depends on the temperature. Okay, so if they give the value of delta H and delta S at a particular temperature, they are asking spontaneity. So you can find spontaneity using what? Delta G. First, using delta H and delta S, find delta G. It can tells you which is spontaneous process or not. Okay, clear? Good. The next thing, I am coming to equilibrium. Again, this chapter gives us 3 questions, right? Mole give us 2 questions almost. Atomic structure also give 2. Mole I will say 2 to 3. Thermodynamics give you 2 almost. Equilibrium give you 3 questions. As the syllabus is reduced, so their advantage, their weightage is increased, right? Now the next thing is, if we discuss little bit about equilibrium. Right, first thing is, what is the meaning of equilibrium? If we start, like A is there, A we have B, maybe 2B, depending on that. At time 0, imagine we started with 10 mole per liter, and it is how much? 0. But at the time of equilibrium, what happened? It is how much? It is 6 molar, it become 8 molar. And after attaining this, you see 6 molar and how much? 8 molar. Now they stopped changing because the rate with which A convert to B and the rate with which B convert to what? A becomes same. So I can say that state in the reaction when rate of forward equals to rate of backward, we call it what? We call it equilibrium. This is known as equilibrium, right? When the rate of forward reaction equals to rate of backward reaction. Just look at this carefully. Are the concentration of forward and backward, are the concentration of reactant and product are same? Are the concentration of reactant and product are same? No, these are not same. These are unequal. So concentration of reactant and product should be equal at equilibrium. No, it is not a condition. What should be same? Rate only. The rate of forward reaction should be equal to rate of backward reaction. Otherwise, the other things are not a condition. Be careful about it, right? The concentration of reactant and product are equal, unequal, we don't care. At equilibrium, rate of forward reaction and rate of backward reaction should be equal, and the observable properties will stop changing. Means partial pressure, concentrations of everything, and or you can say like if I say density, color, smell, these all properties become constant, right? And you can say that the next point you can say, after attaining equilibrium, ratio of the concentration of reactants and products will become constant, right? And observable properties will stop changing. It looks like everything stopped, but no, equilibrium is dynamic in nature. It will continue in forward direction as well as backward direction. It is dynamic in nature, it is not static. Be clear about this statement. I am saying once again, equilibrium is dynamic in nature, not static, right? Okay. Fine. Now the next thing is okay. Now a very small point comes in this, the characteristics of equilibrium, right? Characteristics of you can say, first of all, let me tell you a small point, classification I am telling you. You can classify equilibrium into or more types. I am saying classification. You can divide in 2. One is which one? Physical equilibrium. One is chemical, right? In physical equilibrium and in the chemical equilibrium, you see only change of physical state. I am giving example, S2 liquid and S2 vapors at equilibrium. So no chemical change, only physical state change. Chemical, I divide in further 2 parts. One is molecular equilibrium, in which molecules takes part. Like if I give example, CaCO3 give us what? CaO and what? CO2. Whereas if I go for the ionic equilibrium, so in this ions will come. Like I can say that if I am having acetic acid and I dissolve in water, so ions will be involved here. Like if I show It is CH3 COO minus and plus what? H3O plus, right? So in this case, what is coming? Molecules. In this case, what is coming? Ions. That's why it is ionic equilibrium. And as chemical reaction is happening, so it is part of which one? Chemical equilibrium, right? Whereas here, only physical state is changing. So if only physical state is changing, but the chemical formula is same only, so it is physical equilibrium. If we discuss about the characteristics of equilibrium constant, or I will say equilibrium only. So as I said, at equilibrium, rates of forward and backward will be the same. Second thing, observable properties become constant, stop changing. It is dynamic in nature, and the ratio of the concentration of reactants and products become constant. The next thing is, if equilibrium is involving gases, you can attain such type of equilibrium in only closed vessels. And next you can say catalyst will not affect the equilibrium point. It can just help to attain equilibrium in less time, in small time, right? Or you can say it is dynamic in nature, right? We have done these things. So this is it about this one. What is homogeneous equilibrium? Equilibrium in which all the reactants and products are in same physical state. Maybe all are gases, maybe all are aqueous. So these are homogeneous equilibrium. If some of the reactant or product is in different phase, maybe one or two are gas, one becomes solid. If there are 2 or 3 physical phases are present, physical states are present in the equilibrium reaction, what do we call it? Heterogeneous equilibrium. Like CaCO3 solid give us CaO solid plus CO2 gas, heterogeneous. Ammonia give us N2 gas, H2 gas, ammonia gas, everything gas. So it is which one? Homogeneous equilibrium, right? So the next thing is, you can say law of mass action, right? A small point if I say. Law of mass action means if you are writing some reaction here, I am saying 3A is giving some product. So you say the rate of this reaction will be proportional to the concentration of what? Reactant taken. And instead of saying concentration, they say what? Active mass. You can say rate will be proportional to concentration, you can say, of reactant, or you can say what? Active mass. They are saying mass, but actually it is not mass, it is just concentration, right? By the name it is mass only, but otherwise what is it? N by V. Okay? And one very important thing, they ask active mass for many things. STP, if we have a gas at STP, whatever amount they give, its active mass always how much? 1 by 22.4. Otherwise, for remaining things you can find N by V. Active mass of pure liquids and solids is taken as what? 1. For remaining things you can find, if they give something like you get the moles, you know the volume, N by V is active mass. Otherwise, for pure liquid and solid, always how much? 1 you will take. Fine? Done? The next thing is, you know very well, by the law of chemical equilibrium, you can say, what is Kc? If I write a reaction here, imagine if I am writing a reaction, the reaction is A, B here, giving us what? C and D, right? So what is the Kc value here? Kc value is C concentration, D concentration, power D, A concentration what? A, and B what? Power B, right? Now if you go for Kp, what is Kp beta? Kp is pressure of C, power C, pressure of D, power D here, pressure of A, power what? A, and here we have pressure of B, power B. These are the partial pressure of different components, whereas these are the concentration of different components. These are the concentrations at the time of equilibrium, and these are the partial pressures at the time of equilibrium. Remember, not initial, not final, at the time of equilibrium. So be careful about it, right? This comes from law of chemical equilibrium, right? Fine. If we relate them, if we say relationship between Kp and Kc, if I say we have relationship between what? Kp and Kc, so we can relate it, because Kp equals to what? Kc RT power what? Delta Ng. Delta Ng again, what is delta Ng? Gaseous moles in product side minus gaseous moles in reactant side, right? Normally we take Kp in which units? ATM. ATM C plus D minus A plus B. Kc we take in which units? Mole per liter. What is it here? C plus D minus what? A plus B. So by chance if they are asking numerical, then what R value I should use? You can see here ATM, here mole per liter. So please take 0.0821 in terms of ATM and liter. To make it little small, you can use which one? 1 by 12. To make it small, you can use which one? 1 by 12 to save some of your time, right? Don't use 25 by 3 here. Actually, it depends on units. If they don't mention, it is understood by default that it is ATM, it is mole per liter. So use it accordingly. Like a small question I am asking, which comes many times. I am saying we have a reaction here, and 2A of gas is in equilibrium with 3B of gas, right? So my question is, if I am writing that Kc is equals to Kp RT power x, so our question is, what is x? Students in hurry make mistake. They think, okay, delta Ng 1 only, so 1, no, they reversed it. If you see carefully, they put Kp here, Kc here. So if you put carefully, look at this. Actually Kp equals to Kc RT delta Ng, that is 1, we can see 3 minus 2, 1. But they reverse the question. If you solve it, Kc, Kp, what is coming? RT power minus 1. So carefully give the answer. Here x is not 1, how much? Minus 1. It is minus 1. Be careful. They reversed it. Actual formula is Kp equals to Kc RT power delta Ng. Don't make this type of mistakes. Okay, easy question, but be careful. Avoid silly mistakes in the paper, right? Next thing, if I go, I will take a small example here for one question of Kc. Imagine we have 2A and here we have 3B, and giving us, you can imagine, okay, I am taking B here, right? And here we have 3C times 0. I am saying here we have it is 5 molar, it is also 5 molar, it is 0 molar. And at the time of equilibrium, I am saying it is remaining, how much I am saying? I am saying it is remaining 3 molar, or I am saying 1 molar. You have to find their concentrations at equilibrium and then find what? Then find Kc also. Question is find Kc. They gave initial concentration, they are asking you final concentration, right? Then using the final concentration at the time of equilibrium, what they are asking? They are asking you which one? They are asking Kc. You can see how much reduced? 4. You can see 2 needs 1. So 4 needs how much? 2. So how much remaining? 3. 2 makes 3. 2 makes 3. So 4 makes how much? 6. Right? So now I have the concentration of everything. So we can see the Kc. What is coming Kc? 6 power 3 divided by 1 power 2 and 3 power 1. So simply we can find our question. Yes everyone, got the point? And one more thing, we will have question classes also. We will have question marathon, in which we will discuss one day almost 100 questions of physical chemistry, one day 100 of inorganic, and one day 100 questions of organic. So we will spend more time in questions that day, right? Now the next thing is, if I talk about simple question of same type of question I am saying about Kp, it is 2 ammonia I am giving here, it's N2 3H2, right? At the time 0, what they are saying, at time 0 we are having here imagine 5 atm pressure, it's 5 atm pressure, 0 0. At the time of equilibrium they are saying it is 1 atm pressure remaining. So by the stoichiometry find the final pressure of these things and find the Kp. Just like the concentration questions, exactly same way you can go for the questions of pressure. How much decrease? 4 atm. 2 makes how much? 1. 4 makes how much? 2. That's it. 2 makes how much? 3. 4 makes how much? 6. Now we have pressure of everything. So Kp we can find easily. 2 power 1, 6 power 3, and 1 power how much? 2. So this way easily you can solve your question. Put the point, right? Done. That's it. Now let us come to the Lee Chatelier principle. Okay, so we are having Lee Chatelier principle. What this principle say, beta? This principle say that if you disturb the equilibrium of a reaction, reaction will try to attain it back. If you change any condition which can disturb the equilibrium, reaction will do something, or reaction will move forward or backward to again attain its equilibrium. If you change concentration, pressure, you can say volume or anything, so reaction will try to attain its equilibrium back. And the main thing is, none of the changes in the following factors can change the Kp Kc value except temperature. Very important question. Only temperature is the factor which can change the Kp Kc value. No other factor can change the Kp Kc value. Be careful about it. Right? Got the point? I'm saying once again, some of these factors can disturb the equilibrium, but they can't change the equilibrium point or Kp Kc point. But temperature can change the equilibrium point and the Kp Kc value as well. No other factor. So if we change any factor which disturbs the equilibrium, reaction will try to retrieve it back by going forward or backward. How it will do this? If we look at this bit a little bit, right? How it can do that? If you look at this, if you increase the reactant concentration, imagine you increase the reactant concentration, so reaction go where? Forward, right? If you increase the product concentration, reaction go where? Backward, to again decrease it. Whatever you will do, reaction will do reverse of it, right? Similarly, if you increase the pressure, reaction go where? Where gaseous moles are what? Less. If you decrease the pressure, reaction go where? Gaseous moles are more. If you increase the volume suddenly of the reaction at equilibrium, reaction go where? Gas moles are more. If you decrease the volume, reaction go where? Gas moles are less, right? Whereas fourth point, if I say, catalyst will not affect equilibrium. Catalyst will not disturb even, will not disturb equilibrium. No effect, you can say. We'll say in short, no effect, right? The next point, if I say, fifth point, we can plan better. Fifth point, addition of inert gas. if you add inert gas, what you will do? Addition of inert gas, you say if you do it at constant volume, if you add inert gas at constant volume, then you will say no effect will come, right? But if you add inert gas at constant pressure, in such scenario we have to increase the volume to keep pressure constant, and that's why reaction go where gas moles are more, right? So this way you can see some factors. And one more factor, if I say 6th one, temperature factor depend on the type of reaction. Now if you increase temperature, reaction go which side? Endothermic side. Whatever side is endothermic, reaction will go that side. Whereas if you decrease temperature, reaction go which side? Exothermic side. Where it can be forward, backward depending on the reaction. Fine, clear? I can take one of the example. Imagine I am having example of N2, what here? S2 and 2 ammonia, right? I am saying the delta H is negative, means forward is negative, so backward which one? Positive. Fine. Now let us see. If suddenly I increase the concentration of A, what will happen? If I increase the pressure, what will happen? If I increase the volume, what will happen? Catalyst addition will do what? Catalyst addition. Or if I say helium gas addition, I am saying helium gas addition at what? At constant volume. I am saying at constant volume. So very easy, you can answer better. Increase in concentration of a reactant, reaction go where? Forward. Pressure increase beta. What do we have? Pressure increase. Pressure increase, send it where? Where gas moles are less. Gas mole less where? Again forward by chance. Volume increase, send where? Where gas moles are more. Where gas moles are more? Backward. Very, very important. Catalyst addition, no effect. It can help to attain equilibrium fast, but if it is already at equilibrium, then no effect. Helium gas addition at constant volume, you can say no effect, right? If you increase temperature, reaction go where? Backside, because backside is what? Endothermic. High temperature push toward the endothermic side, whereas low temperature push toward the exothermic side. In this section, forward is what? Exo. Backward is endo. So high temperature favor which one? Backside. Less temperature for which one? Forward side. This is about your Lee-Chatelier principle, right? More questions we will see in the question marathon class. Fine. Now the next thing, if you see beta, let us see the pH questions. Now try to find pH. Find pH of following. They are saying find pH of following, right? How we can find the pH beta? If you see carefully, what do we have? First thing, I am saying we are having 10 to power minus 3 molar HCl solution. I am saying we are having 10 to power minus 8 molar HCl solution. Okay, just for a little revision, if I say what is pH? pH is minus of log of what? H plus. pH is minus of log of H plus. How much H plus is present in your solution, it gives you your pH, right? So if you know this, this is pH. What is pOH? pOH is minus of log of OH concentration, right? And what is Kw? Kw is concentration of H into what? OH. So I can say the pKw equals to what? pH plus pH, right? And this pKW value can change with temperature, but if you say, I can say at 298 Kelvin, the Kw value is 10 to the power how much? Minus 14. So from here we can say that pH plus pH equals to how much? 14. Scale of 14 will work here. So from here to here, 0 to 14, our pH scale work at 200 Kelvin, and is 7 is neutral point, below 7 acidic, and above 7 what? Basic. Above 7 is what? Basic, right? Got the point? Next thing is, okay, let us come to the questions again. We can see very clearly 10 to the power minus 3 molar HCl, strong HCl will ionize completely, give us what? H plus. 10 to the power minus 3 H plus will come here, and that's why I can say H plus is 10 to the power how much? Minus 3. So pH how much coming? 3. In this case, it is very less in concentration, so H plus will not be just 10 to the power minus 8, because water also gives how much? 10 to the power minus 7. It is not the exact data, but approximately we can take that 10 to the power minus 7 H plus is coming from water also, no? Now you can ask, sir, why I am not taking water H plus here? Because water H plus is negligible in this case. H plus given by HCl is very high, H plus given by the water is negligible. You just remember one thing, that it is an acid solution, so its pH will not be 8, pH will be less than 7. That is enough for us to remember, or almost 7. I can say pH is almost how much? 6.96, 6.97. If you are having an acid solution, pH will be less than 7 definitely, if I am talking about 298 Kelvin, right? What is the point? Whereas if you go for the weak acid solutions, right? If we discuss about the weak acid solution, then how we find the pH beta? Ka was C alpha square, right? And H plus was how much? C alpha. So pH formula we have done already. What was it? Half pKa minus of what? Log C. Okay. Whereas if you go for the weak base solution, how we can find the pH? The Kb is C alpha square, and OH minus is how much? C alpha, right? So how we can find pH? The formula of pH is how much? 1 by 2 pKb minus of what? Log C. So use this shortcut to find the pH of weak acid or weak base solution, right? The next thing, if I say it's a weak acid, weak base, in strong acid, strong base, ionize it completely, because strong acid, strong base ionize completely. So from there find H and OH and then find pH. In weak acid, weak base, use this formula to find the pH. Now if you go for the salt solution, or you see the topic they gave salt hydrolysis, right? In salt hydrolysis, what they are saying, in salt hydrolysis they will say find the pH of this solution. Imagine first type, salt of strong acid, strong base, so always pH is beta 7. Salt of strong acid, strong base, pH 7, right? If I take salt of what? Imagine weak acid, strong base. If we have a salt of weak acid, strong base, what is pH in this case? pH is what? 7. How much here? 7 plus half pKa plus what? Log C. pKa plus log C. But if you take the salt of weak base, strong acid, then the pH formula become what? pH equals to what? 7 minus of half pKb plus what? Log C. Why? Because here acid is strong, so less than 7. Here base is strong, so more than 7. Here both are strong, so 7. And remember, here none of these is doing salt hydrolysis. Here this is doing salt hydrolysis, or I can say hydrolysis, and this is doing what? Hydrolysis. In this case anionic hydrolysis, in this case which one? Cationic hydrolysis. Whereas if you take fourth type, you can say it is salt of what? Weak acid and weak base. In such case, pH formula will be 7 plus half pKa minus what? pKb. Salt of weak acid, weak base. So both will do hydrolysis. This type of salt gives us cationic as well as anionic hydrolysis. I'm saying once again, only those ions can do hydrolysis which are part of weak acid or weak base. Or I can say which makes what? Weak acid or weak base. Like NaOH, HCl. These ions make strong acid, strong base. They can't do salt hydrolysis, or they can't do hydrolysis in water. Only those ions can do hydrolysis which are part of weak acid or weak base. Right? That's it. Now, if we come to the buffer, you see, buffer solution are those solutions which resist change in its pH. The buffer solution are those solutions which resist change in its pH, right? If we talk about this one, buffer solution, so I am taking here like this one, first one if I talk. You can take single substance buffer, right? We have a single substance buffer. So single substance buffer is actually salt of what beta? Salt of weak acid and what? Weak base. I can talk about here, you can take like HCO and H4. Just now I have seen. Salt of weak acid, weak base. And the pH you know very well. The pH formula is how much? 7 plus what? Half pKa minus pKb. Just now we have seen, right? Last type of salt act as a buffer which resists change in its pH. Now if you talk about the mixed buffer, there are two type of buffers we know in this. One is which one? Acidic buffer. One is beta acidic buffer, and acidic buffer have formula of pH equals to what? pKa plus log salt by acid. Be careful, always take normality of salt, not the molarity. Take normality, because I need ions here, not the salt. I need ion, common ion which is with the acid, right? And same thing if you go with the basic buffer, the formula of POH equals to what? pKb plus what? Log what here? Salt by base. You will take a log salt by base. Fine. What is the point? This is acidic buffer. This is basic buffer. If I say example, acidic buffer is made up of a weak acid and it's a salt with a strong base, right? Whereas a basic buffer is made up of what? A weak base and its salt with a strong acid, right? Weak base and its salt, weak acid and salt with strong base. Fine, bache. And now we have small thing here. We have here solubility product, right? Now we have here solubility product. So you will have this type of salt. Imagine I have a salt AXBY. It will ionize and give you what? Give you X ions of A and give Y ions of what? B. And they will say KSP. First of all, what is KSP? Concentration of A ions power x as coefficient here, concentration of what? B ions, what power here? Y. So what is KSP? When you dissolve a springly soluble salt in water, ions will come, then the ions concentration and the number coefficient, stoichiometric coefficient as what? Power. This is your KSP. And S here, this is the concentration of ions in what? Mole per liter. If you are dissolving in pure water, if we are dissolving in pure water, means no common ion present, then what will happen? In such case, you will say shortcut KSP equals to x power x here, y power y here, and s power what? X plus y. Okay, like if I take one example here, imagine they are saying find KSP of AgCl if solubility of AgCl, if solubility of AgCl is what? Is 10 to the power minus 4. So what you will say? It is which type? A1, B1, na? So KSP is what coming, beta? Relation of KSP 1 power 1, 1 power 1, S power how much? 2. So S power 10 to the power minus 4 square. How much coming? 10 to the power minus 8. Right? Or one question I can say, reverse way. Find solubility of Ag2. Find solubility of Ag2CrO4 in pure water if KSP is how much? 10 to the power, if I am saying here, just to make it little easy, I am saying it is 4 10 to the power minus 12. Imagine this is given to us, right? What I will do? I will write a relationship here. What's coming? KSP is equals to 2 power 2, 1 power 1, S power 2 plus 1, how much? 3. 4, 4 cancel. S coming how much? 10 to the power minus 4 mole per liter, right? This way you can find. Presence of common ions can decrease the solubility of salts or solutes in the water. More the common ion present, lesser the solubility of the salt, right? The common ion effect also important. So remember, more the common ion present already in the solution, the solubility become less. Like if I dissolve AgCl in NaCl solution where NaCl already present, so AgCl become less soluble. More the NaCl concentration already in solution, lesser the solubility of AgCl, right? So common ion decrease the solubility, right? Clear bachche? Done? Okay. Now let us see a little bit about solutions. Again, expected question are almost 2 from here, right? In solutions, if you see, the first thing is they are discussing about type of solutions. Depending on the physical state of solute and solvent, you can divide it in 9 types, right? Like liquid and liquid, liquid and solid, liquid and gas, gas and liquid, gas and gas, gas and solid, right? So many things are there. 9 types. Like example, if I give, if I say sugar in water, so sugar in water is what? Solid and liquid, right? If even I am saying zinc amalgam, what is that? Mercury in solid, means liquid and solid, right? Air, what is air? Gas and gas. There are 9 type of solutions. They can ask by giving a solution which type of solution it is, right? So coming to the main point here, I am coming to Henry law, right? So what we have in the Henry law, what it is saying, beta, see carefully. a gas will be more soluble in the liquid if pressure of the same gas is high above the solution. Or reverse way, partial pressure of a gas will be high if mole fraction of gas in the solution is high. And here what is it? Henry constant. And every year they are asking question. Last year also they asked question from here, from Henry law. I'm saying once again, more the solubility of gas in the solution, higher will be the partial pressure of gas over this solution, right? If I'm saying this is PA, and here what is it? XA. More pressure, more solubility. More solubility means more pressure. Directly, indirectly, you can say same thing, right? This is Henry constant. If a Henry constant of a gas is high at a given constant pressure, so solubility of gas become whatever, less. It was the last year question. They gave three gases their KH values. They asked their solubility. Higher the KH value, lesser the solubility. Like if I, out of the given gases, helium gas, KH value is very high. That's why solubility is what? Very less. Or I can say what? Minimum here, right? Clear? So next thing is, if you increase temperature, actually increase of temperature, increase the KH value of a gas, and that's why temperature increase, indirectly decrease what? Solubility, right? Again a very simple question. A small question we can see, if I'm asking like, what is the question? They are saying partial pressure of CO2 gas they have given to us. Partial pressure of CO2 gas is 0.1 atm, imagine. It's 0.1 atm, and they're asking the partial, and they're asking the mole fraction of CO2 in this solution. They're asking mole fraction of CO2 in the solution. This is our question. And what is given to us? They have given to us that Henry constant of CO2 is 5 by 3 kilo atm. I am saying kilo atm. So be careful, it's kilo atm, not just atm. So partial pressure how much? 0.1. KH how much? 5 by 3 kilo atm is how much? 10 to the power 3. They are asking the mole fraction of what? CO2. So it's easy to find. Mole fraction of CO2, how much coming? 3 by 5 will go upside. So 3 by 5, 10 to the power how much coming? Minus 4. That's it. Be careful. I will not take total pressure. I will take the partial pressure of CO2. If I am checking about the solubility of CO2, then I will take the partial pressure of CO2. I will not take the total pressure. Maybe many gases are present here. Only partial pressure of CO2 will decide solubility of what? CO2. Partial pressure of O2 will decide partial pressure of solubility of O2. Helium's pressure will decide solubility of helium. Okay, so be careful about it. If by chance they gave lot of gases here, so first by the Dalton's law find the partial pressure of CO2 gas, then apply the formula. You can't take total pressure here. In this question, though, I gave simply CO2 pressure only. But if they gave total pressure of many gases, then find partial pressure of the CO2 gas, then apply the Henry constant, right? Henry law help us in many things, like in cold drinks, we are increasing solubility of CO2 gas by applying high pressure, right? And in other things also, it helps to avoid bends in its application, if you see, right? And you feel nausea if you go to in hill stations. So all these points depends on the Henry law. Now the next thing is, if I am discussing here, is Raoult's law. Raoult's law are also very important, right? What is Raoult's law? Imagine I am having a solution. I am having a solution of A and B. There are two liquids, A and B, both are volatile. Now here A of vapors of A coming, vapors of B coming, and I am saying both are volatile. Here both are volatile. Who both beta? Which one? A as well as B. Both components are beta, right? So they are saying that mole fraction of A is XA air and mole fraction of B is what? XB. Here some of the pressure is created by what? A vapors, and some of the pressure is made by which one? B vapors. So it is PA and PB here, right? So how we can find PA? Actually, vapor pressure of A is proportional to what? The mole fraction of A in the liquid state in the solution. So if you remove the proportionality sign and put here what? Constant, that is P naught A. P naught A is the vapor pressure of A in pure state when B was not present here. This is the Raoult's law. Similarly, PB is what? P naught B into what? XB, right? This is again Raoult's law. I'm saying once again, vapor pressure of A, partial pressure of A, or you can say vapor pressure of A will be directly proportional to the mole fraction of A in the solution. And similarly, which one? B also. I can find PT from here, total pressure. What is that? PA plus what? PB. What's PA here? I can say XA P naught A. And what here? XB P naught B. Fine. Now you see what we are doing. If you keep B, XB as 1 minus XA, because sum of the mole fractions is equals to what? 1, right? So I can write this way also, that PT, we can write this way also, that it is P naught B equals to what? P naught A minus what? P naught B into XA. In terms of mole fraction of A only. How I am solving it, how I am writing it, I am just putting what? I am putting XB as what? I am putting XB as 1 minus XA. Right? Nothing else. 1 minus XA. And similarly, I can say PT is what? P naught A equals to what? P naught B minus what? P naught A and what here? XB. So if they are giving you this type of question, so relate this with the given data to get the P naught B, and then what? P naught A, P naught minus B, right? And the next thing is YA. In vapor phase, YA and YB is the mole fraction of A and B. In vapor phase, what is that? YA. YA is, you can say PA by PT. And what is YB? YB is PB by PT, right? That's it. So now imagine I'm giving a solution. I'm giving a question here, A and B. Form an ideal solution. A and B form an ideal solution. So here you see, I'm saying total pressure expression is given. PT is given as 200 plus 120 XA. This is given. And they are saying find P naught A and what? P naught B. This is given to us, right? So by this expression, you have to find the P naught A and P naught B. You see carefully, they have given the expression only in terms of what? XA. So you can take help of this one. What is coming? I can say PT equals to what? P naught B plus what? P naught A minus P naught B XA. Relate it. P naught B this one, and this whole is which one? 120. So I can say P naught B will become how much? 200. And P naught A minus P naught B is coming how much? 120. Right? So I can say from here P naught A is coming how much? 320 mm of Hg. In this type of question it will help that way. Clear, right? This is about your Raoult's law, and definitely Raoult's law is applicable only for which? Ideal solutions only. For non-ideal solutions it will not be applicable, or I can say those solutions which do not follow Raoult's law will be non-ideal solutions. Non-ideal solutions can be further of two types, one having positive deviation and one having negative deviation, right? So solutions having positive deviation, when solute-solute interactions and solvent-solvent interaction, you know that when solute and solvent interaction will be weaker than solute-solute or solvent-solvent, this type of solution will be having non-ideal and positive deviation. Whereas if solute-solvent interactions are stronger than the solute-solute and solvent-solvent, it will make which one? It will make non-ideal solution with negative deviation. Like alcohol plus water are the best example of non-ideal solution with positive deviation, and acid plus water are best examples of non-ideal solutions with the negative deviation. Solutions with positive deviation will or can form minimum boiling azeotropes at some proper ratio of both the components, and solutions with negative deviation can form maximum boiling azeotropes at some proper concentration, like 68% HNO3 with water makes what? Maximum boiling azeotrope, whereas 95% almost ethanol and water mixture makes what? Positive deviation azeotrope, or you can say minimum boiling azeotrope, right? Minimum boiling azeotrope will have boiling point less than both the components, whereas maximum boiling azeotrope will have boiling point more than both the components. And azeotrope components can't be separated using fractional distillation. So sometimes it's very common question, they give 4 options and they say which of these can be separated using the fractional distillation. You have to find option which is making ideal solution, because solutions which are non-ideal, maybe positive deviation, maybe negative deviation, they will form azeotropes, and after forming azeotrope you can't separate them from each other. So if you want to separate something by fractional distillation, out of the following 4 options, find option which is making ideal solution, right? Okay, that's it. Now the next point is colligative properties. Fine. There are 4 colligative properties. Right? There are 4 colligative properties in our syllabus here. First of all, what is the meaning of colligative properties? These are the properties of solution which depends on the number of solute particles present and do not depend on the nature of solute. I am saying once again, properties value of which depends on the number of solute particles, not on the nature of solute particles, right? We are having here 4 properties, like first if I say relative lowering of vapor pressure, second was you can say elevation of boiling point, and the third one you can say is depression in freezing point, and the next I will say is osmotic pressure. Next is osmotic pressure, right? Clear? Before starting about these properties, you should know about the little bit about Van 't Hoff factor, right? Van 't Hoff factor is I. Right? Van 't Hoff factor, if there is no association, no dissociation, I is 1. But if there is dissociation, then I is more than 1. If there is association, I is what? Less than 1. What is the formula of I? I in case of dissociation have formula 1 minus alpha plus n alpha. And in case of I, association is 1 minus alpha plus what? Alpha by n. Okay. What is alpha here? Degree of dissociation or degree of association. And what is n? Here n is number of particles given by one particle on dissociation. And what is n here? Number of particles associated together to make a bigger particle, right? If alpha is not given, but you know that it will ionize in solution, like if I put NaCl in water and I am not giving its alpha, so you can take alpha as 1. If NaCl give 2 ions, so what will be the bond factor? 2. If they gave alpha, then so you have to use alpha and use the formula. If they don't give alpha, but you know very well, array, it is the ionic thing and it will ionize definitely. So you can take alpha by yourself 1. Like CaCl2. CaCl2 give how many particles? 3 particles. So what is I value? 3. So if you see here, I am saying once again, what is I? You can say number of particles. Number of particles after dissociation or association. And here we have number of particles before association or dissociation, right? So first of all, our target is to find what? Bond factor before using or going for any of these properties. What is RLVP? We know very well beta. RLVP is P naught minus PS divided by P naught. But don't forget about I, XB. What is XB? XB is the mole fraction of non-volatile solute, right? Now, what is the elevation in boiling point? It is TB minus TB naught equals to what? I kbm. It is I kbm. And what is depression in freezing point? Delta TF, or I will say TF naught minus what? TF equals to what? I kfm. And here osmotic pressure means what? Pi equals to ICRT. If I is more, then all of these properties will be what? High. Clear? So now try to understand this very carefully. You know very well what is the mole fraction, what is the molarity, and you can put the formula very easily. But one thing is very important. Look at this. Remember, if for a question, for a solution, RLVP is coming high. If for a solution, RLVP is coming high, so remember, RLVP high means vapor pressure of solution is what? Less. This value high means this value is what? Less. Be careful. If elevation in boiling point is high, so boiling point of solution will be what? High. Right? And if delta TF is high, so be careful. Freezing point of solution will be very less. Right? And the next thing, so osmotic pressure, you can say simply, osmotic pressure to is no such question can come from here. In osmotic pressure, what is the important point? If I repeat one more here, isotonic solution. What is isotonic solutions? Those which have same osmotic pressure. I can say pi 1 equals to what? Pi 2. Or I can say I1 C1 equals to what? I2 C2. I1 C1 equals to I2 C2. Right? Clear, bache? Done? So next thing, if I say, one question I am giving to discuss all these properties, like compare RLVP, delta TB, delta TF and osmotic pressure for given solutions. Right? Imagine I am having here 0.1 molar urea solution. Here I am having 0.1 molar NaCl solution. Here we are having 0.1 molar CaCl2 solution, and here we have 0.1 molar K4 FeCN6 solution, right? So they can ask question from any of these. They can ask which of these have the highest osmotic pressure, highest boiling point, freezing point, like this one, right? So if I ask you, first of all, tell me which one have the highest RLVP? Tell me, beta. You see, na, if molarity is more, then mole fraction will be more. We know relationship, right? So if molarity is more, mole fraction is more. That we can go. But molarity given same, so mole fraction also same in all cases. But here the Von Tau factor, how much, beta? I is 1. Here what is I? I is 2. What is I? Von Tau factor how much? 3. And what is I here? I is 5. So Von Tau factor will change all the scenario. Okay, right? So Ix more, I into I more means RLVP more, delta TB more, delta TF more, osmotic pressure more, right? Basically, तो multiplication tell us, I into M will tell us, or I into X will tell us. But here, M is same, X is same. So who is the main factor? Von Tau factor, right? That's why you can say which one has the highest value, beta. Fourth has the highest value. Then which one? Third, then second, then first. For every property, I can say for RLVP, I can say for delta TB, I can say for delta TF also, and which one also? Osmotic pressure, right? But if I ask you, now if by chance they change the question, they ask which one of these have the highest vapor pressure? You see, RLVP is minimum here. Now in first case, RLVP will be what? Minimum. So here vapor pressure is what? Maximum. So first is the answer. If they ask me which one have the highest freezing point, I can say in first case delta TF is what? Minimum. So definitely delta TF minimum is what? TF highest. So first will have highest highest vapor pressure and highest freezing point. So be careful what they are asking. They are asking RLVP highest, or they are asking vapor pressure solution highest, or they are asking delta TF highest, or they are asking TF highest. I am saying once again, this one have highest delta TF. Depression and freezing point is highest, but here freezing point of solution is highest. So be careful about these 4 or 5 points, bache. Clear, right? Okay, bache. I hope you will get a benefit from the lecture, and some of the remaining points, some of the important questions I will discuss in the upcoming question marathon. In that we will discuss question from electrochemistry and kinetics also, and we will try to cover all the remaining important points through that marathon. Okay, as I told you, after the 3 hours these theory classes, we will have 3 extra classes for questions, in which we will cover the most important 100 questions of every branch of chemistry, that is physical, inorganic and organic. Okay, so stay tuned. Okay bache, bye, thank you very much, see you soon.